Hello, everyone, and welcome to my talk, the GCP Jenga Tower, hacking millions of Google servers with a single package and more. What if I told you that the requests that you see here are from internal Google servers? That was the moment that I realized I ran code on all of these servers, and I can potentially run code on millions of servers. That was without any interaction at all until I got blocked. And guess what? Google was not the one who was responsible for blocking me. So please say hi to the CloudImposer vulnerability. That vulnerability discovery has led me to realize a concept that is present in the major cloud providers. I named this concept Jenga. Cloud providers build their services on top of each other, just like Jenga. It allows for unique privilege escalation and, spoiler alert, even vulnerabilities. That Jenga concept realization has also led me to discover a new novel privilege escalation vulnerability in GCP Cloud Functions, a serverless execution environment that runs code in response to events. So enough with the teaser. I am Liv Matan, a senior security researcher at Tenable. I am Microsoft's most valuable researcher. And as you can see or might assume, I also hunt across the major cloud providers, and it includes some of the past notable published research, some of the vulnerability names like emoji deploy, flow fixation, and today we're going to talk about confused function and CloudImposer. So supply chain attacks, we all know them. They are dangerous. But supply chain attacks in the cloud are boosted, kind of like on steroids. For example, one malicious package that happens to be deployed in an on-prem server will only affect that on-prem server, as opposed to one malicious package that will happen to be deployed to a cloud service that will be deployed to millions. Just imagine the blast radius of such a vulnerability. We can take it into a more practical example and look at these statistics of the Apache Airflow package in Python. The Apache Airflow open source system is a system that handles data pipelines and workflows. So you can see at the left side of the screen, this package, as for June 2024, was downloaded almost 22 million times. And as for the recent month, almost 26 million times. So we can apply these statistics and estimate how many vulnerable users will be in GCP Composer, the managed service, the managed version of Apache Airflow in GCP. So before we get into the vulnerability, the CloudImposer technical details, the vulnerability itself, let's start with the prequel. The prequel to this vulnerability was the concept, the attack technique that Alex Bearson has discovered and named dependency confusion. So as you can see on the screen, an innocent user or an application is just tries to install an innocent package from his own private registry. And it does so by using this pip install command and by using this extra index URL argument. What he doesn't know that this extra index URL argument also searches for other indexes, other Python indexes in that case. Some of them is the public registry, PyPI. So in that case, an attacker might take the opportunity in order to upload a malicious package with the same name, in that case named legit package, but with malicious code inside this package. So pip is now getting confused because, as the extra index URL told him, search also for the public registry, but he sees two packages with the same name. And in that specific case, in the dependency confusion attack, the legit package has the version of 0.2. And in the requirement.txt, you can see in the left bottom of the screen, the required version to be installed should be greater than 0.1. But the attacker, in that case, has the opportunity to upload a package with a higher version, thus take over the installation process of the victim. So that is dependency confusion very briefly, but stay with me and keep in mind that the CloudImposer vulnerability case study is a unique case study of dependency confusion and something you haven't seen before. So we can conclude that package managers are dangerous. Python and the extra index URL argument is just one example of such a risk of dependency confusion. This risk also affects NPM and other package managers. So I researched Google Cloud Function, and I noticed that documentation that guides users into using private dependencies from the artifact registry service. And as you can see, Google themselves guide users into using this risky extra index URL argument. But I didn't stop here. I decided to use Google dorking in order to find more instances of this false guidance of users, of Google guides, that guides users into using this risky argument. And I found the Google Cloud App Engine, also another misconfiguration of a false documentation that guides users into using this argument. Not only that, also GCP Composer. What the hell did just happen? These are 3 services that Google advises users, advised in the past, I will correct myself, to use this extra index URL argument, and you saw how dangerous this argument is and how risky it is. And we can now know that there are a lot of GCP customers that follow this guidance and are now vulnerable to dependency confusion. So Google is a bug bounty platform. They are a very good company. What did happen? I continued the research, and I saw that these are actually misconfigurations followed by other misconfigurations. So following the Google's documentation, I saw this line that says, if you want to learn more about installing private packages, please go and see the Python packaging documentation. I went ahead and saw this Python packaging user guide, and guess what? It tells, if you want to host your own simple repository, please guide users into using the extra index URL argument. So we can now assume that Google followed this Python guide, and these were misconfigurations followed by other misconfigurations. So I reported this false guidance by Python as well to Python, which shared with me this PEP 708 that tells extending the repo API to mitigate dependency confusion attacks. So this thread was created in 20 February 2023. We are in 2024, and this issue is still a real threat. This thread, no one took any action in order to resolve it, and this is still open. So CloudImposer, it all started here. I had a lot of teasers. Let's get into it. How does it really work? So you see, this is another Google's documentation, but that time it helped me to discover CloudImposer. So as you can see, this is Cloud Composer 2 images. I, as an ordinary user, can create a GCP Composer service. And when I create it, I remind you, this is just a managed Apache Airflow service. So when I create it, I deploy GCP Composer image. And that image is simply an Apache Airflow system image that is also bundled with PyPI packages. And these PyPI packages, some of them include Google's internal packages. And as researchers, after talking about dependency confusion, I was curious to see maybe I can confuse the process of each GCP Composer service in the world, that each GCP Composer in the world installs the same PyPI packages we just see in the documentation. So I had an idea. These are pre-installed dependencies. These dependencies are installed in each GCP Composer service. Why not scan those? So I went ahead, I used this silly code you see on the screen. Not really, this is just a mock-up. But I tried to search for missing packages from the public registry, specifically packages that are installed on each GCP Composer deployment or update. And then I found this. I will highlight this for you. This is the package of Google Cloud Data Catalog Lineage Producer Client, the package of Google, internal package of Google. And this package is trying to be installed on each GCP Composer service deployment. We saw it in the Google's documentation, so it's not in the public repo. Where is this package? So the next step for me is to dive into the GCP Composer file system. I ran code on my own GCP Composer, and I grabbed the file system to find some metadata or something that will reveal information for me as a researcher of this package, this internal Google package. And I found this metadata dist file that simply reveals to me that the package installation process behind the scenes works as such. Pip install -- extra index URL, Google's own private repo, and this Google Cloud Data Catalog lineage producer client package. So we have all of the ingredients. The package of Google themselves is missing from the public registry. And also, the installation process is using this extra index URL argument we just saw is very, very risky. But not so easy and not so fast. The research continues, and I went back into Google's documentation to then see this line that specifies that this package is actually version pinned. So let's confuse it even more. So in that case, as you can see, this is the same process, but now in Google Cloud's own service in GCP Composer. GCP is confused because the pip install is using the extra index URL argument, and now it has to choose between two packages with the same name and the same version. This is much more confusing. GCP has to choose between the package of the attacker from the PyPI public repo or Google Cloud's own package, the private package. So if the package that will be chosen wasn't the malicious package of the attacker, I will simply not stand here on this blacked stage. So, yep. In that case, also when the version is pinned and also when two versions are the exact same versions and the names are the exact same, pip will prioritize the public repo. Then a user named Felix said, what's going on? This was in 2018. How is it possible that pip with the extra index URL argument always prioritizes the public PyPI? The answer was, this is not likely to change. The answer was from one of the contributors of the Python Software Foundation. And yeah, this was in 2018. We are in 2024. Dependency confusion is still a threat. The next step for me is to emulate. I emulated the process again. I ran code on my own GCP Composer service, and I ran this pip install with the extra index URL argument, this risky argument, and the private registry of Google. Then I saw that pip is looking for two indexes, the public one and the private one, and it chose the public one. The next step was to craft the POC. Again, this is just a mock-up code. The intention of the code is to try and validate that the code is actually being run in the Google's environment, in Google's internal servers, or the customer environments. And it says, CURL, please give hits. The next step was to actually upload the package of Google with the name of the package of Google's internal package and the same version. And the next step was to see all of these hits and just jump in the chair because I was so excited to see those. But then this happened. Sorry, something went wrong. So to comply with the bug bounty rules, as a researcher, I went into PyPI in order to remove the package, delete it from PyPI, and also delete my user. That was in a matter of seconds. And it said to me after visiting PyPI, PyPI is down for maintenance or is having an outage. And I'm going to tell you a secret between us. PyPI was not down for maintenance. PyPI actually blocked me, my user, and also the package that I just uploaded in a matter of seconds. My speculation were that there is a defense mechanism I'm not aware of, or there is a PyPI partnership with Google. Thank you. So I reported the vulnerability CloudImposer to Google, which classified it as remote code execution and awarded a bounty for it. Google fixed the vulnerable script that was utilizing this extra index URL argument we have talked about that we now know is very risky. And Google also checked the checksum of the vulnerable package instances in order to find any evidence of the vulnerability exploitation in the past. Google said that there is no evidence for the vulnerability exploitation in the past after they checked the scenario. Also, for transparency, Google said that the package that I uploaded for the POC hit Google's internal servers, but as for Google's customer environments, they believe the package won't pass the integration tests. Google also decided to fix the documentation issues and now guides users into using the index URL argument. And as opposed to the extra index URL argument, this argument tells pip to only search for the specified registry that was given as a value to this argument. So the confusion cannot happen with this argument. Also, Google is now advising users into using the artifact registry virtual repo to safely control the order that pip searches for repositories. That was as a result of the report I reported to Google, and I told them, use your own feature. That feature can help you in order to prevent and mitigate dependency confusion attacks. OK, so we've talked about the CloudImposer vulnerability. We now know the risks of dependency confusion and much more. But let's go beyond remote code execution. We had a remote code execution. We had a POC. But what can we actually do with it? So back to the Jenga concept we have talked about, cloud providers build their services on top of each other. And in that case, GCP Composer is built on Google Kubernetes Engine, another Google's service. So the Jenga concept comes into play, and I can abuse the Google Kubernetes Engine service architecture in order to escalate privileges and do some more fun stuff. If you want to learn more about it, make sure to visit our Tenable blog, because a blog about the vulnerability, and this as well, will soon be published. So we've talked about CloudImposer, the Jenga, and now with the Jenga concept in mind, let's find some more vulnerabilities, specifically in GCP. And I remind you, the Jenga concept not only affects GCP. This is just one example, but it affects the major cloud providers. Have you ever pondered with the question of what is going on when you create a cloud function in GCP? Well, I had. A lot of stuff are going on behind the scenes. So I created a cloud function, an innocent one, as an ordinary user. And I saw this cloud build odd trigger in the Logs Explorer in GCP. Turns out that this cloud build trigger was initiated and created by the cloud function I just created. And not only that, also a bucket was created, an artifact registry, or a container registry, and possibly event arc triggers and Cloud Run. These were all the services that were created behind the scenes by Google, kind of without my users' knowledge. And this is absolutely crazy, because I can edit those services, I can see those, but not really, because this process was happening behind the scenes. If I wasn't researching cloud functions or not looking at the logs deeply, I wouldn't be able to see those services that were spawned in order to help the function deploy. It creates risks. For example, an attacker with access to a Cloud Run service, and that Cloud Run service by default has access to the artifact registry or a container registry. And these services, guess what, holds the images of the functions in the same account. So these concepts allowed for new privilege escalation paths, some that you see right now, and soon a new vulnerability will be revealed. So just a brief on the function deployment flow, so we will be on the same page. This is the Cloud Function deployment flow. It creates resources, as we saw, some of them bucket to store the function's code, an artifact registry to store the function's image, a cloud build to build the function, and a Cloud Run service to run the function. It all makes sense. These services are there to deploy the function. Google also decided to attach the Cloud Build default service account to the Cloud Build service. And this default service account is very, very risky and what caused the vulnerability. To those of you who are not familiar, a service account in GCP is an identity that you attach to an application or a service in order to allow this service to communicate with other services. Makes sense. And in that case, Google attached this service account in order to allow the Cloud Build to push the image to the artifact registry. It has to have this permission. Please say hi to a new privilege escalation vulnerability I dubbed confused function. It allows an identity with a permission to update or create a function to escalate permissions to this default cloud-built service account we just inspected. These are all of the permissions of the default cloud-built service account, and I'm sure you are not going to see all of those from far away, but trust me, these are a lot of permissions. Some of them include permissions to storage, logging, artifact registry, buckets, and more. How does it really work? Let's go into the technical details of the vulnerability, the fun stuff. First, an attacker with a permission to update a cloud function. In this example, a specific example, I'm going to show you an example of a Node.js cloud function, but obviously this vulnerability affects all of the programming languages. This is just a concept. So in that case, an attacker will update the package.json file of the function. And that package.json file specifies the dependencies that will be installed soon. So the function's code will be stored in a bucket. This bucket will then, this bucket object will then be pulled by the cloud-built instance. And some of this is the function's code, and some of the function code is the package.json file that specifies the dependencies that should be installed. Well, in that package.json file, there is a malicious dependency that the attacker has just inserted. And then, with just the permission to update a function, the attacker could insert a malicious dependency that will be installed in the cloud-built instance. And as we know, Google, by default, has attached this cloud-built default service account to this cloud build that helps the deployment of the function. Thus, I can run code and exfiltrate this identity in order to escalate my permissions. This was just with a simple malicious dependency that I insert into the file that is specifying dependencies that will be installed in the cloud-built instance. To those of you who still didn't really follow, this is a graph we made for you, an identity with a permission to update a function, update the function, then cloud-built instance will get the malicious dependency that was just specified in the cloud functions file from the PyPI registry. This is an example of a Python exploitation. Then the cloud-built instance code that was just ran, the malicious code, will provide the cloud-built service account credentials to the malicious attacker server. As for the fix, Google now allows the use of custom service accounts in Cloud Function. These custom service accounts are the custom service accounts of the cloud build that is created as a result of the function's deployment. So now, when you create a new cloud function in Google Cloud, you are able to choose two service accounts. One is the service account of the functions itself, and second is the service account of the cloud build that is created as a part of the function's deployment process. Before the fix, the user didn't have any visibility to the cloud build service account that was created behind the scenes. Also, Google has decided to now use the compute engine service account as a new default for new cloud builds. We can now know that old cloud builds, as a result of the fix, or not as a result of the fix, but old cloud builds are still vulnerable. Some thoughts on the fix is that there are still minimum permissions for the custom cloud build service account to even work. So even if now users have the ability to choose a custom cloud build service account, they still need to provide these permissions. And these permissions are still rather powerful. So we can say that the vulnerability, the confused function vulnerability, still exists in a kind of manner, so this is still risky. For example, the artifact registry .writer permission has to be given to this cloud build service account, to the custom cloud build service account, and this permission is rather powerful. But it makes sense because this architecture of the function should have this permission, because the cloud build service account should have the permission to push the function's image into the cloud build service, into the artifact registry service. It makes sense. Also, the compute engine default service account is notorious for being overprivileged. We all know that. So these are the thoughts on the fix. I'm going to reveal a new tool we named the Jenganizer that was developed by my fellow researcher, Noam Dahan. And this tool allows you to find and discover hidden services that AWS deploys behind the scenes when you create a new service in AWS. This is just one example of the tool in AWS, but we plan to expand this tool to GCP and Azure. So what does this tool actually do is that you create a service, for example, a cloud function, then you run the tool. And when you run the tool, it allows you to discover these hidden services that were created as a result of this process. So in AWS, when you create a Lambda, you can run the tool and see the hidden services that AWS creates behind the scenes as a result of creating this Lambda function. Isn't it crazy? Because as researchers, you can now maybe discover even new vulnerabilities as a result of this hidden services creation process. Or as defenders, you now have the visibility to see these hidden services and defend from new privilege escalations or vulnerabilities. So you can go ahead and scan the QR code if you are interested in this. This is how the tool looks when you run it. You supply a username, the profile name, the region name, and you can also supply a time start and time end in order to allow the tool to only look for the action that you want to look at. And for example, as you can see on the screen, this is a CloudFormation stack just for the sake of the example, not in any attacker's perspective or something. But as you saw, this stack creates an EC2 run instances. So this is how the tool works. You can also choose the depth level of the tool to make it even more recursive. So for example, if these services, the EC2 service creates more services after the creation of the EC2, you will see it with depth level 2. And if these services that were just created by the EC2 creates even more services, you will see it with depth level 3. As for GCP, for now, you can use this GCP log explorer example. This is the query I used in order to find the hidden services that were created after a creation of a cloud function. So I saw that a cloud build and a GCS bucket were created as a result of the cloud function creation. So this query is very, very handful. To wrap up, one click in the console or in anything in the API that you want to create a service in a cloud provider results in the cloud provider that configures a vulnerable deployment to the user. This is rather risky, and in order to combat this scenario, we can use the Jenganizer tool or simply look in the logs in order to find these hidden services. Cloud providers also sometimes get it wrong. We saw it in the CloudImposer vulnerability and in a confused function vulnerability. Cloud providers are not bulletproof, and we keep seeing this, so please take care. Supply chain attacks in the cloud are boosted. We saw it. They are on steroids. Like, millions of users were potentially could be affected of the CloudImposer vulnerability, and this is just one example of supply chain attack in the cloud. Imagine what could happen in future supply chain attacks. So supply chain attacks in the cloud are rather wild. Dependency confusion. Please beware, because this concept, this attack technique, was there for years. And we also saw this GitHub thread from 2018. It is 2024, and we should be more aware of this risk, of dependency confusion risk. So 3 takeaways I have for you for today. First, how to protect yourself from dependency confusion risk. You should check for the package installation process in your environments. Specifically in Python, you can use the index URL argument instead of the extra index URL argument. As we saw, this is a safe argument as opposed to the extra index URL argument that also looks for the public registry and opens the door for attackers for dependency confusion. The second takeaway for you is how to protect yourself from confused function. The confused function vulnerability, we saw that still kind of lives. You should go ahead and replace every Cloud Function service account, specifically the cloud-based service account, with a least privileged service account. We follow the least privilege model, and we give the permissions that we saw, the minimum permissions that are required for this custom cloud-based service account, as opposed to using the default cloud-based service account that has rather highly permissive permissions. The third takeaway is that there is a gap in the shared responsibility model. Know your services, because we saw that there are a lot of hidden services we are not aware of. Cloud providers are kind of a black box. The cloud is a black box. There are a lot of hidden services, and we should be aware of them. But these services are in your environment. You can edit those, you can see those, you can delete those. But some of these services are kind of hidden. So I hope you now have the right tools to search and combat this huge thing called cloud that is essentially a black box. Thank you. Any questions? Yep, sure.
Is there any consideration you have to think of between version 1 and version 2 of the cloud functions, or does the same vulnerabilities apply?
So the confuse function actually affects also the first gen of cloud functions. So there's not really consideration, but in the second generation of cloud function, it also possibly creates event arc triggers, as you saw. So there might be more resources combining into this step of the functions deployment process, but it isn't related to the confuse function vulnerability.
Thank you.
No problem. Yep.
So the package which you published, was it just doing request.get? Because I'm just wondering, like, why did it get blocked?
Can you say again, please?
So the package which you published, was it just doing request.get to your server? I'm just wondering, like, why did it get blocked?
Yeah. So the package that I uploaded sent HTTP requests to my server, and it got blocked in a matter of seconds. It was like literally 20 seconds after I logged into PyPI in order to block my own package, and it already got blocked.
OK, so they must have some internal testing.
This is just speculations. Yeah,
okay.
These are just speculations.
You mentioned that one of the fixes that Google did was to replace the default cloud build service account with the compute engine service account. But how does that actually improve the situation? Because as you said, the compute engine service account also has a ton of permissions.
Yep. So this is actually a question for Google. This is very controversial. In my opinion, the compute engine service account as a default is already used in GCP services. So I think this is a nice fallback for them to now use it, because people are kind of aware of this compute engine service account. They might have organization policies that helps to combat this default. This is just my take on that fix. OK. Thank you, everyone. Thank you for welcoming me into the Blackhat stage. And if you have any more questions, I will be in the wrap room.